Thank you very much. So it's great to see everybody here, and congratulations for surviving until this last talk. I hope to deliver on that setup. So I'm going to be spending most of my time talking about quantum Monte Carlo methods. So in contrast to what we've seen through most of this workshop, these are stochastic methods. So we're going to be using random numbers to go after the whole many-body Schrodinger equation, as opposed to doing lots of numerical integrals. So that's one big difference, and that actually buys us the ability to tackle these very difficult problems. These are methods that I did my PhD on quite a few years ago now, and I then went away and did about 100 papers in density functional theory and also more empirical methods. But recently I've come back to these because for a couple of reasons. One is that we're seeing that we really need them, particularly for systems such as transition metal oxides, where we have lots of questions about the accuracy of DFT and very sparse experimental data. And then secondly, these are methods that can really benefit from increased computer power. So they very naturally scale onto the larger machines that are coming along. Now, I don't have much time to talk about exascale in this talk, but what I aim to do is give a few pieces of food for thought to everyone in this room, regardless of whether you're interested in quantum Monte Carlo or not. So some things to think about in order to use these larger machines that are coming along. And of course, in the interim, before coming back, it actually turns out the algorithms have also gotten a lot better. And that's also key. We need science-based algorithms improving these methods to get the additional accuracy that we're after. So the outline of this talk is really straightforward. I'm going to describe a little bit of the motivation for these methods and their history. And then I'm going to spend most of my time talking about real space quantum Monte Carlo methods, because these are the most used for complex materials systems. And then rather than simply make claims, I'm going to spend some time showing you published work showing what can be done today, and then use that to lead into what we might look forward to in the future with advances in high-performance computing, that's HPC, and then what then needs to happen in quantum Monte Carlo. So just by way of background, I'd like you to think back to a slide that Matthias showed 12 days ago or so now. Right? So this is the slide which has got length scale vertically against the time scale. And of course, there's a lot of properties up here in the top right in the continuum that we want to get to. And we have to build up to that, starting from robust electronic structure theory methods. So this talk is going to be about the beyond density functional theory, through ab initio and through a variety of classical techniques really to build up. And one of the motivations for quantum Monte Carlo is really stated at the bottom here, is that we want robust and error-controlled links between all these methods. So in this talk, we're going to be focusing down here, length scales of maybe nanometers. And actually, I do promise you I'm going to show some dynamics at the end, so we will have a time scale in this talk. We'll have some picoseconds at least. And what we really want to do is provide a really solid foundation for the rest of this enterprise. And of course, what we're really doing here is attempting to meet a Dirac's challenge. So remember, we have the full complexity of the Schrodinger equation, including the very difficult electron-electron part. And of course, we are really challenged to develop approximate practical methods of applying these. And actually, we'll see how far we can get in solving these directly, because that's what we're going to do. And before going much further, I think I should show probably what's still the most famous and most important quantum Monte Carlo result for electronic structure, right, which is actually now 37 years old. And this is the work by David Seppeley and Bernie Alder, PRL 1980. what is it? So it's the energy, essentially, on this vertical axis against a density, that's this RS value, of the homogeneous electron gas. So this is a box full of electrons, essentially. And the key thing, so here's a result here, and you have error bars. We have a statistical method. And the key thing about this work is that it's exact. It's a special form of the fixed node diffusion Monte Carlo that I'll be explaining later. This is a release node form that makes it exact. Now, unfortunately, it's brutally exponential, this method, so we're not going to be applying it to real materials anytime soon. But for the homogeneous electron gas, it is indeed exact. And of course, it's famously parameterized in the appendix of this paper by Perdue and Zunger, which is, of course, actually about what's wrong with the LDA. So for many of the functionals that we're using in DFT, we still have some dependence on this data. So we're reliant on this. And so that brings us to what's our challenge, what are our goals? Right? What we want to do then is solve the many-body Schrödinger equation, and crucially, with only readily controllable approximations. Perhaps we can't do an exact calculation like I just showed you, but we want to have a knob, right, where if we pay more, we get steadily more accurate results. And the key thing is that this has to be an accurate and tractable method. We want to get understanding from it, and then we want to provide usually useful benchmarks for other methods, particularly actually periodic systems, because we respect the quantum chemists very much. They've done a very good job solving for isolated molecular systems, but what we currently lack is a good convergent method for solids, and that's what we're working towards. And of course, once we have this data, of course, it's very clear from the other talks at this conference that we can do various forms of upscaling. We could machine learn, we could build a new functional, all sorts of things. So this would be very useful. Now, you might be thinking, well, why don't I just validate with respect to experiment? And of course, we're definitely going to do that, but as we've heard, we have to be careful in how we do this, because sometimes the interpretation is a little ambiguous, and so I'm showing three particular concerns that we might have here. So on the left here, sometimes the experimental interpretation is unclear. So this is the case of the phase diagram of Titania, so TiO2. And the problem is right on the front of this book, The Collector's Guide to the 3 Phases of Titania. So there are 3 naturally occurring phases of titania that you can dig out of the ground: rutile, anatase, and brookite. We see they're not pure from all the colors here, but clearly these can't all be the ground state, right? 1 must be the ground state and 2 must be metastable. But these are certainly metastable enough to sit around in the lab for a long time. So, of course, what we learn, this is actually quite a religious topic, there's growth conditions very much complicate which phase is going to be stable. And that actually means it's quite hard to infer what should be happening at 0 temperature in DFT or even quantum Monte Carlo for that case. And this is quite a famous problem. Of course, if we've gone off and predicted a new material, which we'd certainly like to be in the business of doing, by definition, there's going to be no experimental data available, so we can't immediately validate. Sometimes a synthesis might be very difficult or costly. And then, of course, DFT is also used very widely. So this is not a materials example, but it's a measure of the success of the method. So this is Juno, just going around Jupiter at the minute. So Jupiter is hydrogen, helium. And by looking at the drag on the satellite, they've been able to infer information essentially about the phase diagram and the composition. And so there are papers comparing the models of the planet against ab initio computer simulations. And those computer simulations are today density functional theory, and they don't exactly agree with the measurements, right? And clearly it's quite expensive to go off and do some more measurements, so we need to do a very good job on the theory side. Now, of course, the theory situation isn't perfect either. So, of course, there's now this zoo of different density functional theories that we can use out there. This is from Master Swart's DFT poll. And of course, for some particular material, perhaps all these functionals are good, perhaps they're all bad, right? We don't necessarily know a priori. More formally, probably people familiar with this recent paper, it's been observed, and this is actually well worth reading and looking at the comment and reply, that some of the recent, let's say, more empirically developed functionals, while they may have improved the energy, haven't simultaneously improved the density. And that's a bit of a worry since we're doing density functional theory. And of course, this is actually interesting to us because the density is actually very easy to get from quantum Monte Carlo. So what are we going to do? Well, we need some kind of reckoning. Now, of course, Stefano Cottarolo showed some motivation from the good, the bad, and the ugly. And don't worry, Matthias, you're quite safe in this reference. There's a very tense scene at the very start of Once Upon a Time in the West, which is the next film made by Sergio Leone. And for anyone in this room who's actually seen this film, if you think about the dialogue during the scene, you'll know exactly why I am showing this. For anyone who hasn't, just remember, this is a Western. All right, so what about real space quantum Monte Carlo? So I'm going to start with variational Monte Carlo, which is a very simple method and is really a direct application of a textbook technique. And I should emphasize that it is useful for research purposes. So I can point to research papers this year directly using variational Monte Carlo. So what do we do? Well, what do we remember? We can just evaluate the energy of a trial wave function, and I'm going to say where we get this from on the next slide, right? This is just psi h psi over mod psi squared. So this is quantum mechanics 101, right? I'll say more about this trial wave function. There's a convenient quantity I'm going to use in quantum Monte Carlo, which is called the local energy, which is just h psi over psi. So this is just a number. And then there's a very nice trick. Up here, you basically insert and divide by psi t over t, psi t. And when you write this down, you have the integral of mod psi squared times the local energy over the integral of mod psi squared. And if we look at this quantity that's outlined in red, we see that it's positive definite and it's normalized. So that means it's a probability density, and so we can do textbook Metropolis Monte Carlo on this, very straightforwardly. Now, of course, it's not quite textbook Monte Carlo, because if we have 1,000 electrons, they're each moving in x, y, and z in free space, so this is a 3,000 dimensional integral. But everything that applies when you first learn Monte Carlo on, say, a 6-dimensional problem just carries over here. And of course, there's lots of numerical tricks to make this efficient, but the fundamentals of the method is just here. And of course, we're going to rely on the variational property that we also learn in quantum mechanics 101 here, and make different guesses at the wave function, and then we know that lower energy results are closer to the ground state and improved. So what might we do in a modern calculation? So here I've written down an example of a sort of state-of-the-art wave function. And so what it is here, we take the best quantum chemistry wave function that you can afford. So I've shown here, for example, a ground state slated determinant, say Hartree-Fock, a bunch of singles, a bunch of doubles. So this is a configuration interaction expansion, which we learned about in Eagle's lecture. And of course, this has got lots of parameters and coefficients in it that we may change later on to improve this wave function. And then we multiply this by a real space term. And this is actually where we build in a lot of physics. So for example, we know that when electrons come together, there should be a cusp in the wave function. This is what makes raw configuration interactions, expansions, very slow to converge. In variational Monte Carlo, we just build it in analytically. Right? You can put electronuclear cusps and so on as well. and essentially build in a lot of physics to overall improve the many-body wave function. And so an example of something that's actually used, this is one from the Casino code in the paper in 2004. What we have is functions of electron-electron positions, this functions of electron-ion. Here is a three-body term, and so on. And these are all short-ranged polynomials with a number of parameters in that we're going to optimize. So this is a way of writing down a highly parameterized wave function, but building in some physics directly that we don't otherwise get from quantum chemistry methods. Now, I'm going to show how well this works in a few slides. Let's just review what we've got here. So what are the advantages of this method, particularly as compared to the method I'm going to show you next? Well, we have an explicit form of the trial wave function. This is actually very useful. It makes it relatively easy to compute any observable, because we can just do the integral. Okay. And we can also do very simple Monte Carlo, so there's no other discretization or errors here. The disadvantage, though, is essentially the same as the advantage, right? We've got this explicit form of the trial wave function, so we're limited to what we can imagine, right? We can put in a pairing wave function in here, a backflow BCS, whatever gives rise to a lower energy. But this is hard to do for a complex material. And so we tend to have lots and lots of parameterized to optimize, maybe thousands, tens of thousands. We'd like to do millions. And so this is one of the real challenges of applying variational Monte Carlo to complex systems, how to optimize all these parameters reliably. So it would be nice to have a method that's less dependent on what we put into it. And so we use projection methods. And so this is diffusion quantum Monte Carlo, which I think is the most used for real materials problems. And so this is a many-body wave function projection method, and it doesn't have a strong, let's say, dependence on the input trial wave function. And the high-level outline is here, and it's actually very simple. So what we do is we write the time-dependent Schrödinger equation in imaginary time. So tau is I times t, right? And this we should now recognize as a very easy partial differential equation that we know how to solve, right? And if we put in some eigenstates, we'll end up with something like this. If we now think about what happens at increased time, what's going to happen is that the higher energy excited states are going to disappear exponentially faster than the lowest energy state. That's what this exponential up here is doing. Of course, we have to remember to keep this normalized so we don't also lose the ground state, but that turns out to be easy. So that's very high level what happens in diffusion quantum Monte Carlo. Now, when one turns it into Monte Carlo, it actually has a very elegant mapping onto a Monte Carlo walk, but with a variable number of Markov chains. So at one time step, we might have 1,000. At the next time step, we might have 1,020, for example. It varies. One nice thing when you do this is that you can reuse essentially all the code you had in variational Monte Carlo. It reuses a lot of the machinery. And unfortunately, that's not quite the end of the story. There's one problem with this, a very famous problem, and that's the fermion sign problem. If we just naively apply this to our wave functions, they will zoom down not to the fermionic ground state, but to the bosonic ground state. And what we need is a fermionic solution where if we interchange two electron positions, the wave function changes sign, right? That's one of the marks of fermion. So what's done is to use a so-called fixed node approximation. And this introduces a variational error in the energy. So we're going to be able to test this in just the same way that we tested our variational Monte Carlo wave function. And so what we do is we take an approximate nodal surface, so the zeros of a wave function, and we take these from the next best available method. So that could be variational Monte Carlo, if we've done a particularly good job, or it could be DFT, Hartree-Fock, or quantum chemistry. That's the basics of diffusion quantum Monte Carlo. If we do this, we actually have quite a nice method. I mentioned it's variational. We like these properties. They're testable. We're going to see it's very accurate. It's notionally cubic scaling in terms of moving the electrons, but depending on the statistical properties of what you're measuring, that scaling can actually vary from, say, squared to n to the fourth. And as we'll see later on, this happens to map very, very nicely onto large machines. So I'm not going to read all these advantages and disadvantages of diffusion Monte Carlo. These are for reference. We're going to see that this is a very accurate method, even with quite simple trial wave functions. So for example, using trial wave functions from DFT works very well. Slightly surprising. The bigger disadvantage is the cost. It's at least an order of magnitude more expensive than variational Monte Carlo. And part of the reason is that we have this time step, this time evolution. We've got to propagate these wave functions. And to do it accurately, we need quite small time steps. There's a Trotter decomposition in the application of the Green's function. If we think about the errors and approximations, though, the nice thing is that potentially they're all controllable. So the main systematic error is the fixed node error here, fixed node boundary condition, which is variational. So we can test this or develop some optimization scheme. And there are actually some in the literature that do this directly. We, of course, have some sort of technical errors that we have to worry about with really any calculation. So, for example, have we done a big enough supercell to make the finite size errors small enough? We have to do finite size scaling, periodic calculations. Is the time step small enough? Unfortunately, this kind of error is something that the larger computers are very much helping with. So these errors are essentially automatically getting smaller as the computers grow. We would like in better algorithms to converge even faster, of course, but this is a help. And then finally, I think it's always worth thinking about this for any electronic structure method. We have to be very careful that we solve the right Hamiltonian. There's no point in having an exact solution of the wrong Hamiltonian, right? So, for example, if we use a shooter potential, that needs to be good enough for the job. And similarly, if we have a system with spin-orbit interaction, we better make sure to put that in the Hamiltonian. So let's now see how this actually fares today. And I'm going to start with molecular results. So what I'm showing on this graph are some accuracy results for the G1 test set. So this is a series of small organics, atoms, dimers, trimers, I think. And what this shows is the mean error of the atomization energy in kcal per mole. And the colors are different methods, and I'm going to talk through this in a moment. This dashed line is the not yet good enough, but still hard enough target of 1 kcal per mole, or so-called chemical accuracy. We would, of course, like better than that for all methods. And I should say here that the key thing to achieving this was a very important new algorithm developed by Cyrus Umrigar in about 2007. It's called the linear method, sometimes called energy minimization, and it what makes the systematic convergence that I'm about to talk through reliable and very repeatable. Okay, so what am I showing here, right, in these different colors? So this on the left is the main really result. These blue bars are diffusion quantum Monte Carlo. This one on the left is a single determinant, so we see the error is 3 kcal per mole. And moving to the right, we're taking ever more determinants in our wave function, and we are optimizing the coefficients in front of the determinants. We're not doing full orbital optimization yet. So we're optimizing the coefficients in front of the singles, the doubles, triples, and so on. And what we see is as we work harder, essentially, we get lower errors, and eventually we get below the 1 kcal per mole target accuracy. Interestingly, if we do this for variational Monte Carlo, it's a much simpler method. We start off with a higher error. We can get down to 3 kcal per mole or so. We could have kept working, but that's actually pretty good considering we have now essentially an analytic form for that wave function. Of course, the quantum chemists also work in this area. So if you do couple cluster with F12 and good basis sets and work hard enough, you get to chemal accuracy as well, really below here. Of course, perturbation theory is less good, and DFT is essentially as good as the functional that you've chosen or how it's been fit. Let me show a couple of research examples to show some of the sophistication that's going on. So this is a study by Claudia Filippi and co-workers. It's already about 7 years old now. This is calculations on model retinal chromophores, so some of the molecules that are shown here. And what the paper does is look at excited state properties of these molecules. So we can not only do ground states, we can do excited states. And there's full structural relaxation of these molecules. And some of the analysis is shown here. So we see the variation in bond lengths. And the analysis is at the few hundredths of an angstrom level. So this is a very high precision study. Of course, this work, you do a lot of comparisons with quantum chemistry. And the significance of this paper was that a different photoisomerization mechanism was proposed than what I think was conventional wisdom. And actually, since this has been done, Claudia Filippi and co-workers have done a lot of follow-on work, for example, with polarizable embedding and considerations of size consistency. You want to make sure that the errors are consistent as we do larger and larger molecules. That has to be worked out for these many-body wave functions. So this is really a very sophisticated study. Let me show another example. And this is really a different philosophy. And this is from the Toulouse Quantum Monte Carlo group, Michel Caffarel and co-workers. And the idea here is that they're not going to do any of this stochastic optimization, which we used in the last couple of slides. What we're going to do is take a full configuration interaction result, or the best quantum chemistry we can do, and just post-process it with Diffusion Monte Carlo. So this is push button. You don't need to think very much to do this. So this is a post-full CI method. And significantly, I can't really show this on the graph, is that they have a method. They've been developing a method, configuration, interaction, perturbation, selected iteration, if I remember correctly, which lets you grow CI expansions essentially automatically. So you can say, give me the first 100,000 determinants, and it will do so. So if you do this, what happens? So this is a republished result on the water molecule. So this is energy, and this is I think the previous best full CI result. And this is basis running horizontally. So you see there's quite a strong basis dependence, but you then extrapolate. If you do diffusion Monte Carlo on top, you see that you're immediately lower in energy, right? And in fact, done here, this actually extrapolates to what I think is still the best energy that's been computed for the water dimer. So this is actually very recent work. It's pretty exciting. And several groups, including us, right, are now running Diffusion Monte Carlo with millions of determinants. And we're also doing full re-optimization. So this work isn't published yet, but essentially when you do full optimization, these points get brought down here, the curve is much flatter, and things are faster. So for example, Platinum 2's been run, some tricky spin crossover complexes have been run, and this is very exciting because it's very automatic. So that's the situation with molecules. What I now want to do is move over to talking about solids. Right? And unfortunately, we don't have the same level of machinery in the solids. So we're mostly using single determinant wave functions from well-chosen DFT or Hartree-Fock. There's a few other wave functions that are being used, but most production calculations are using this. We'll see, though, that it works very well. So what I'm showing here is some validation work that was done for a range of metal oxides. You can probably see that this is testing to get ready to do a series of high-temperature cuprate superconductors. So we've got lanthanum oxide, yttrium oxide, scandium, barium, strontium, and calcium. And what's shown here vertically is the error in the cohesive energy, and in the lower part is the error in the lattice constant. The diffusion Monte Carlo is in red, so that's this scatter here, right? And various DFTs are these other bars, right? So we see that the diffusion Monte Carlo, which of course is not exact, right? There's a number of approximations still going on here, is within about a % of experiment, with the provisos about comparing to the right experiments, of course. When we look at the lattice constant, we see actually we're very good for the lighter systems, but something seems to be going on here, and we're like a % off or so in the lattice constant. What could that be? So we have an advantage. We have a method with very few approximations in it, so there's really nowhere for the errors to hide, right? There's only two possibilities here. One is nodal error, and the second, this is a shooter potential calculation, is the shooter potential isn't good enough. And my money would be on the shooter potential for lanthanum, but this hasn't been solved yet. It still needs to be revisited. When we look against the different DFTs, though, we see we're doing really quite well for the energy. So let's do something that's a little bit more difficult. Let's do a Perovskite superlattice. So this is lanthanum ferrite, strontium ferrite, and we're going to be concerned about vacancies and vacancy dynamics in this material. And we're interested in this because we have experimental colleagues down the corridor, and they want to know how the oxygen diffuses in this material. They've also got microscopy. So we've done calculations of the site locations and also some diffusion barriers, which I'm not going to go into here. So on the left, what I'm showing is the neutral oxygen vacancy formation energy under oxygen-rich conditions. So the vacancy formation energies are quite high. The quantum Monte Carlo results are these points on the far right. And these other points are different DFTs which have been used in the literature. And there's a very interesting, this is strontium ferrite at the top and lanthanum ferrite below. And so we see there's quite a scatter in strontium ferrite, is compared with the quantum Monte Carlo, but at least it's straddling. For lanthanum ferrite, though, there seems to be this systematic low formation energy, even for, say, hybrid DFTs. And this is actually very tricky then when you do the superlattice, because, for example, you could argue that you should shift the oxygen potential or the oxygen formation energy, but you can't get a balanced description of both of these materials in the superlattice. So then when one looks at what's stable in the superlattice, which is what's shown here on the right, here's the quantum Monte Carlo results, you see that the position and maybe even the ordering is different from the different DFTs. And this actually has physical consequences, because it means if we then do a kinetic Monte Carlo or some study of oxygen diffusion in this material, both the amount of diffusion is going to vary, and even the diffusion mechanism can vary. So this is actually very significant in this material. Now, of course, we would really like to have experimental values for the formation energies of these defects to validate it against, but they're not available. There are other materials, though, where these are very well studied. So this is looking at the nitrogen defect in zinc oxide. This is a very useful paper from the group of Elif Ertekin at the University of Illinois. And it's very useful, in addition to just the intrinsic interest in zinc oxide, because they do a very thorough discussion and assessment of all the different errors in these calculations. So what they computed here was the zinc-rich conditions, the most stable form of the nitrogen defect. So we see it's neutral for a while and then it's charged. And indeed, if you add up all the different error contributions, you are still close to experiment, or really very close to experiment, but it's actually quite a lot of work. So there's a lot of discussion here that's actually important for doing these calculations in practice. So these are not completely push-button calculations by any means to relate to experiment. So now let's do something more difficult. Let's look at calcium copper oxide. It actually turned out that two QMC groups did the system essentially at the same time. So what we're trying to do here is predict ab initio the exchange coupling, so J, I mean the sort of thing we might have in the Hubbard model, or similar model for these materials, do that ab initio without any fitting. And so to do that, we're going to exploit the variational property of diffusion Monte Carlo. I'd like you to focus here on this top plot. So what we're going to do is we're going to look at the energy difference between ferromagnetic solutions and anti-ferromagnetic solutions. We're going to take the difference, and that's essentially J or 2J, depending on how you set things up. And what we're going to do here is we're going to use DFT plus U calculations, which of course have no variational property associated with them in DFT, but we're going to post-process them in diffusion Monte Carlo. And then we know, formally, that the lowest energy energies are the best ones. So we have a high value of U, we get higher energies, but for a lower value of U, say 1, 2, or 3, we see the ferromagnetic and antiferromagnetic energies are have about stabilized. So then we take the difference, and this is our calculated exchange coupling around here, and this yellow bar indicates the experimental range from neutron scattering. And so we see that the best diffusion Monte Carlo results, which we know from the variational theorem, actually have the best agreement with experiment. So what was nice, I said two groups did it at the same time. They got essentially the same results. And actually, Lucas Wagner, Illinois, has gone on to look at, for example, spin lattice couplings, and also lanthanum copper oxide, some of the other materials. So it's actually quite a surprise that the quantum Monte Carlo at this level of approximation works so well. But these relatively simple wave functions in solid-state systems really do appear to be usefully accurate today. So obviously, we're going to keep applying them. I'd now like to show an example of the Titania conundrum, or the puzzle that I showed earlier. This is actually a case where we're going to have something very good to say about DFT, where there'd been a lot of criticism in the literature. So we were slightly surprised at the results, but this is what we found, and so this is what we're going to report. So the situation here is that the Rutal phase is generally thought to be the most stable phase at ambient conditions, so where we are now. But of course, there's lots of contributions to stability, particularly if you have a nanoparticle, for example, where the surface energies really matter. Most DFTs at 0 temperature find anatase to be the most stable. And there's actually a huge literature claiming that this is a big error. I can point to papers where people are forcing the results they would like, including with more advanced methods than just local GGA. And it turned out that, again, two QMC groups, that's us in the US and also John Trail and co-workers in the UK, did this system at essentially the same time. And one nice thing here, actually, is that this is using different codes and slightly different technical choices. So, for example, the shooter potentials are different. The main difference between the studies is that I would claim that we did larger cells and probably have slightly more reliable finite size extrapolation. But we then looked at quasi-harmonic phonons. The second author of the paper from the UK is Bartholomew Montserrat, and they did anharmonic phonons. And there is actually a contribution from phonon anharmonicity in the system. But nevertheless, at 0 temperature, we both found anatase to be stable. This is shown here. This is the energy against diffusion Monte Carlo. This is from the UK paper. And we see there's actually quite a small energy difference that we're working to here. It's only a few tens of millivolts. Sorry, a few tenths of a volt. And then if we look at different DFTs, we see that pretty robustly, anatase is quite stable. Some of the other phases do shift around depending on what you're doing. And the real trick turned out to be doing the finite temperature calculations well, which hadn't necessarily always been done in the literature. This is done with DFT and just shifting the 0 temperature results with the DMC energies. And we see that somewhere between 400 and 700 or so, that Rutal will become the most stable. So this doesn't completely solve the puzzle, but it's certainly something to think about if you're doing a DFT calculation on the system. You may not want to force this Rutal result, and all these different local DFTs might actually have been okay all along. Now what's really needed to solve this problem Well, what we really need now is cross-validation with some other methods with different approximations, converge, and get essentially the same results as this real space diffusion quantum Monte Carlo. And if these different methods agree, I think we might be able to put this problem to rest. Because of course, these are not exact quantum Monte Carlo calculations. The paper's going to what the errors are. And in future, we want to reduce them and, of course, really make sure, put this to bed. So how are we going to do this cross-validation? Well, I'd now like to switch topics. So I'm going to move away from real space quantum Monte Carlo, and I want to talk about a couple of other methods that have really come on in the last few years and we're really interested in. And those are methods that work either in a determinantal space or an orbital space. So first here I'm showing on the left, there's a new method called full configuration interaction quantum Monte Carlo. And this was, I think, most famously demonstrated in solids in this Nature paper. And also, actually, a key point that some people miss about this paper is that it actually showed that coupled cluster with perturbative triples is actually very good in solids. So that's also a method to keep our eyes on. Full CI quantum Monte Carlo is nearly exact or essentially exact. But to date, it's only really been demonstrated on few atom primitive cell materials. It's a very new method, and there's a lot of ideas and development going on, so we're interested in developing this further. And then a much older method is auxiliary field quantum Monte Carlo, which works in an orbital basis. So a basis of atomic orbitals or natural orbitals, for example. So this is a basis set method. This is a recent paper actually looking at calculating some local properties, so some ground state properties, so an electron density and a spin-spin correlation function. But auxiliary field has been applied to solids, it's been applied to atoms for band gaps, and more. And it seems to have very good errors. And again, it can be systematically improved. So these are very attractive methods to complement real space. One of the reasons is that, for example, you've got some choices about what you do with atomic cores. You can do frozen core very easily. You can put multiple projector shooter potentials in here, or do a PAW if you would like in these methods. And it also makes computation of some observables actually easier than in diffusion quantum Monte Carlo. And actually, to help with this cross-validation, just to show we're taking this seriously, we've just put a new open source implementation of auxiliary field in QMC pack, which is our code, to actually make doing this cross-validation easier. All right, so that's what I wanted to show you about what we can do today. And now I want to talk about what we can look forward to in future. And here I'm going to talk about the growth in high-performance computing. I've just got a couple of slides here. I'll be happy to talk more over lunch or this afternoon if people have got questions. So what I'm showing here is the top 500 list. Probably most people have heard of this. This is a biennially produced list of the fastest computers at solving this LinPack problem, which is essentially linear algebra. And so on the left axis here, we've got the speed of the machine in flops. So 1 petaflop is here, reached in the early 2000s. And we see there's this general trend up and to the right. So this x-axis is the year. These yellow points are the #1 fastest machines. So the current fastest machine is Taihu Light in China. And it's got 10 million processor cores. So to use this machine, you need a lot of parallelization. The same goes for all the other machines as well, I should point out. But that's the direction. What's interesting, though, is that these blue points are the number 500th fastest machine. And you see that they're on basically the same trend as the #1 fastest machine. So this is very interesting because it means, even if we're not fortunate enough to have access to the top machines, the bottom machines are also getting a lot faster. So these are machines that our university or department might be able to get or afford. Let's think about where the #1 machine is heading first. So of course, we're going to reach exascale in 2020, 21 or so, I actually had to remind myself what the next power up is. So zettascale, maybe 12, 15 years after that, if the current trend keeps growing. So that's 1,000 times more computer power. And for doing material science or chemistry, we want to think, how can we exploit that? We don't have to, but certainly other domains are going to be looking to exploit this. Of course, at the same time, the lower end machines are improving. And so today, you can buy a petaflop in a single rack, a big fridge size machine. And that's the sort of thing a university can run. So you can maybe have dedicated access to that. Where is the increased performance coming from? So this isn't shown on this plot, although it's hinted up here. The clock speed is not increasing. This is for power consumption regions and energy efficiency. What's happening is that the core count is going up through miniaturization. So the next machine might have 100 million cores. And also vectorization is becoming increasingly important. There's other things I can talk about, but those are the points I'd like to make here, the key points. So, what does that mean to us? Well, very soon, we're going to have billion-way parallelism on the top machine, right? And this actually, even if we're not using a big machine, we can't really escape from these trends, because these chips are not necessarily going to be special to the HPC machines. So for example, already on Knight's Landing, last year from Intel, there's 68 cores on that chip. And this is important if you're running, because first of all, to fully use the machine, you need 60 MPI or 60 threads to use efficiently. And at least on the machines that I run on, we get charged for the whole chip, whether we use all the cores or not. So if I'm not parallel, I'm wasting 59 of the cores. So 67 if I do this, right? So what I encourage you to think about then is, well, we should think about algorithms then that can scale, right? So for example, sampling algorithms do this very well. So we're doing Monte Carlo. This works well. If we're doing free energy surface exploration with metadynamics of some flavor, that actually certainly makes life easier. And some forms of data analysis also map very well onto these machines. Parallel in time molecular dynamics can also exploit these machines. And something that I would encourage everyone to think about is to really be ambitious. If you try and diagonalize a 1,000 by 1,000 matrix, you're not going to be able to use many nodes of these machines. If you go to millions by millions, you actually have a chance. You've got a hard enough problem. So you need to do hard problems that are also worthwhile science-wise. For those who are developing code, I don't know how many people in this room are doing this, I'd really encourage everyone to use modern software development. These different architectures that are coming along and probably a lot of pressure to write, for example, to write different optimized versions of the code, and I would encourage people to stay away from that because it's not scalable. So we're working on very portable techniques, and there's a real advantage to, I would say, open source here and developing and sharing components of software as opposed to having big monolithic chunks of software, because there's so much to work on that if you can find something common with another research group, another student or postdoc and share, you're going to be more productive. Right? There just simply is not enough time to work on all these problems. How does quantum Monte Carlo scale? This is a benchmark run on Titan, which is a machine at Oak Ridge. It's a GPU machine with about 20,000 nodes, if I remember correctly. This is parallel efficiency, and this is 100% running Titania. We're over 90% on about 90% of the machine. But notice it's not perfect. We've still got some work to do. A smaller graphite problem begins to fall off. Right? So even for quantum Monte Carlo, which has relatively loose parallelism requirements, we still need to do some work. What to look for from quantum Monte Carlo? Well, one thing that I think we're going to really see coming in the next few years is more observables for better comparison with different projects, for different experiments. This is still a relatively new algorithm. There's not necessarily fundamental problems here, so there's lots of student and postdoc projects ready to go. And this will really improve the science that we can do. in terms of technical improvements, key thing to look out for is full optimization of wave functions in the solids, much like we're able to do in molecules right now, because that will mean we have a fully internally self-consistent method, and we'll no longer be post-processing other people's data. That's quite successful, but I think some of the errors we're seeing will essentially go away when we do this. Of course, there's other improvements. In particular, right, we would like to have see forces demonstrated in really complex systems, and also MD. And so that's what I want to show you now. This was presented at the Telluride meeting. So I have to thank Michele Cagula and co-workers at CNRS and the University of Pierre and Marie Curie in Paris for this result. So what am I showing here? So this is an excess proton and 6 waters. And the key point here is the atoms are moving. We have dynamics now. And this study combines very accurate quantum mechanics, thermal effects, and also the nuclei are treated quantum mechanically. So this is beyond Born-Oppenheimer. So this is actually coming a long way to meeting Dirac's challenge, which I showed in one of our early slides. They had to develop a new dynamic scheme to treat the statistical noise on the forces that come here, but this seems to work very well. And I'm not going to steal their thunder. They still need to publish this, but clearly they've seen some very important changes in the dynamics compared with loss comprehensive methods. And one thing that actually I found quite surprising was that the cost of this run was only, quote unquote, only 600,000 CPU hours for 10 picoseconds of dynamics. And for us, we put in supercomputer time proposals for tens of millions of hours. So this is actually pretty affordable in the grand scheme of things. And one can certainly then envisage how in a few years they're going to be doing a lot more water and making a very serious attempt on the excess proton problem in full periodic water. How to find out more? There's some notes here about some of the schools and conferences. There was actually a very good school in Telluride. Unfortunately, this year, you'll need a time machine to go to it because it was last month, but there'll probably be another one in 2019. And with some of the attendees, actually, we had a discussion, should there be a European version just to get a different mix of people, and that's something to explore and work out. We have a QMC Pack summer school coming up next year, and this tends to be advertised on the Psyche email list. So if anyone's not subscribed to that for any reason, I definitely encourage it. There's lots of good electronic structure and use there. We work on the QMC Pack code. This is fully open source. We actually have, you can go to GitHub. We have 34 contributors. That's about to go up another one. We think we're quite fast and validated. There are other codes, but I would encourage you, if you're interested, just to contact the researchers. It's a very friendly community, and I have confidence that if your problem doesn't fit someone's code, but someone else, but maybe it fits us or Champ, for example, that you'll get the right pointer and good feedback. So then, just to conclude, I hope I've shown you that stochastic methods are really a very promising route to doing the full quantum many-body problem. We can apply QMC really to quite some complex systems where we have questions about DFT and think the extra effort is warranted. And finally, we're very much looking forward to cross-validation of different methods. And inevitably, as HPC power increases, we're going to have much more application of these methods. So on that note, thank you very much.